The other type of buffer problem we need to consider is how does the pH change in a buffer after we add acid to it? Because what's the point in making a buffer if you're not going to actually use it and test it out and use it to add acid to and, keep that concentration the same? Because buffers are great in that they resist change in pH. So if you're wanting to do an experiment that's going to produce an acid as a byproduct, but you don't want your pH changing all the time, you would want to do that reaction in a buffered solution. So let's see how this buffer works. So you make a buffer using 0.8 molar hydrofluoric acid, and there's its Ka, and 0.8 molar sodium fluoride. I want to know what's the pH in this solution after I add 0.1 moles of solid potassium hydroxide, to a 1 liter sample of my buffer. So we're going to assume that any hydroxide that I added is going to completely react. Okay, from a stoichiometry standpoint, we're assuming that any sort of base that we add completely reacts with the acid, and then we'll need to make a stoichiometry table and then figure out what our new equilibrium concentrations are. So, first we need to figure out what's the concentration of base that I added. So I was told that it was 0.1 moles and it was a 1 liter sample, so that's a 0.1 molar solution that I added. And then we're going to write the reaction that happens when the acid reacts with a base. Acid plus base makes water and salt. Acid plus base makes water and salt. And we're going to get rid of any spectators. That's why I wrote NaOH like this and NaF like this, right? Because sodium is a spectator. So what's really happening here is hydroxide and HF are reacting to form fluoride and water. Okay, sodium ion is just a spectator. So there's my net ionic equation. And now we're going to set up a stoichiometry table to figure out what happens when I add OH minus. So there's my stoichiometry table. All right, HF plus OH minus makes water and fluoride. So this was originally in there. This was originally in there. And this is what I added, right? We're going to assume that all of the OH minus, all the hydroxide that I add, completely reacts, so it goes all the way down to 0. Because OH is a reactant, that means HF is going to go down by that same amount. And then law of conservation of mass says that if this side goes down by 0.1, this side needs to go up by 0.1. So here are my equilibrium concentrations of fluoride and HF. Now we're just going to use our good old buffer calculation formula, right? Because this is HA and this is A minus, and Ka was given in the problem, so we just plug in Ka times 0.7 divided by 0.9, and then we get this. Now that's only H3O plus though. We need to convert that into a pH by taking the negative log. So my new pH is 3.25. Buffer calculations aren't any more difficult than regular old weak acid problems. They just involve a little bit more thinking sometimes. And that's all that this kind of problem involves. And we're done.